Okay, let's say that you've got a circuit and maybe here's a wire and it's connected to, you've got your battery and your resistor. Don't draw this, but something like this maybe. And at some point, the wire splits to two different pathways. There is a rule that can help us figure out what happens at this junction. It's called Kirchhoff's first law, and it says the sum of current entering the junction equals the sum of current leaving the junction. Or sometimes that's written as sigma I in, the current entering equals the current exiting. Why is that? Well, it's because charges can't just disappear. Charge is conserved. So if you have some charge flowing through the wire, and then you reach this junction, some of the charge will have to take one path, the rest of the charge will have to take the other, and you can't have more on this end than what you started with. You can't create charge out of thin air, and you can't have charge just disappear out of thin air. So this is a statement that charge is conserved. And this is generally true. This is true in all cases. So let me put that at the top maybe. Okay, apply that to this scenario. Let's see. Okay, I1 is going in, so that's on the left side. I1, and it splits. I2 and I3 are going out, so it splits up into I2 and I3. And I put I2 and I3 on the right side because those are the outbound current. Okay, how about this one here? Here's our junction. The sum of the current going in equals the sum of the current going out. So what's going in? Well, this one's going in, so is this one, and so is that one. So you've got I1 plus the second current plus the third current equals how much goes out? 0. So there's different ways you can apply it. We've just practiced two ways. Now let's give it a shot with some actual values here. This picture is actually missing some information. You need to know that there's 0.2 amps traveling along this pathway. Okay, so here's a junction, and you've got some coming in, 0.2. That means how much current do you have here at the other side of the junction? Well, there's 0.6 going in, and you have 0.2 leaving, so there must be another 0.4 leaving, so that the outbound adds up to the inbound. Okay, and then you've got your 0.4 splitting again. Here it splits again. 0.2 goes this way, and another amount goes down. How much is this? That's what I want to figure out. This has to be 0.2 amps traveling through this branch. How do I know? Well, 0.2 plus 0.2 gives the total outbound, which equals the total inbound. So you can think of this as one junction if you'd like. Right? The missing information, remember, was that there was 0.2 right here. Think of this as your junction. 0.6 goes in, and you've got 0.2 splitting off here, here, and here to give a total of the inbound 0.6. And you know that when they all join back up right here, you need the full 0.6 again. Okay, how about this one? What's the current through this first branch? Well, you've got 0.1 branching off this way, 0.2 branching off this way, so that's a total of 0.3. So this has to be 0.3, so that the outbound from the junction, from this junction, equals the inbound going into the junction. Now you might be wondering, why would the current split evenly versus over here where the current splits differently? Well, you may have heard that current takes the path of least resistance. Path of least resistance. And what that means is that this pathway would have to have a lower resistance. And this pathway, where there's not much current, would be a bigger resistance. and this is a lower resistance, and this one's kind of in the middle. Okay, let's learn Kirchhoff's second law. It says the total potential difference around any closed loop is 0. Now, before I write this, I'm first going to just state conservation of energy for the charges moving around. Let's take a charge. Here she is, Mrs. Charge. And let's say that when she moves through the battery, she gains 10 joules for this 1 coulomb, therefore amounting to an EMF of 10. Notice there's no internal resistance. Okay, as this charge goes around, it loses some energy here, and we can see it's going to lose 5 joules, which means when it passes through this resistor, it loses the rest of its energy. Why does it have to lose the rest of its energy? Because when it gets back to here, the battery gives it 10. And you cannot have more energy being created by the circuit than you have dissipated by the circuit. In other words, the energy that the battery puts into the circuit has to be the energy coming out of the circuit. You can't create energy from the circuit just out of thin air. Now we need absolute values to take care of the negative signs, but we'll wait a minute here. If I divide both sides by Q, then what is this? This says the total potential difference in is equal to the total potential difference going out. But what do we call the potential difference? The total potential difference put into a circuit. What is that called? It's called the EMF. And V, the letter V, potential difference, will stand simply for the potential difference consumed by the circuit. Okay, so this is how we are going to write Kirchhoff's second law. It applies to any closed loop. So in this law, you have to draw closed loops. All right, let's apply it right here. You have 10 joules per coulomb as the total EMF around this circuit, around this loop. And how much potential difference is being used up? Well, you've got 5 right here, plus, well, this is an unknown potential difference. Let's call that V1 and V2. And what does V2 have to equal? It must equal 5. And that's Kirchhoff's second law. So here, let's take this closed loop, and let's solve for V1. You don't even need to do any math. I mean, I'll write it out, but the total EMF on the left side, the total EMF around this loop, is just this battery right here, 12. And when we get to V1, that's not known, how much we consume there. And then when we get to V2, that's 8. So what's V1? It must be 4 volts. That's Kirchhoff's second law. Pretty easy. All right, how about this one? Try this loop. Ah, look at this. You can't choose both pathways. The charges have to go around one loop, and then other charges go around the other loop. So just choose one pathway. You've got 6 as the left side of the equation for the total EMF. That means this is the only device right here. This is the only thing that can consume energy. So it must use up all 6 volts. There's nowhere else for the energy to go when you travel through this loop. And likewise, if you choose the second loop, charges come here, they travel through this pathway. We're ignoring the middle one, remember, because we're only considering this loop. You've got the left side of the equation is 6 volts as the total EMF around the loop. And the only thing that consumes potential difference is this resistor right here. So this must be having 6 volts as well. And we just learned something interesting. Whenever you have two different branches like this, current can go this way or this way. That's called, those branches are in parallel. those two resistors are in, parallel. And that's because there's two separate pathways where the charges can flow through, and then they join back up right here. Parallel branches dissipate equal voltage, we've learned. And so that's going to be true even though the resistances are different. Even with different resistances, you still have to consume all 4 volts right here, and then around this loop, you need to consume all 4 volts. And so even there, when the two resistors, the two branches, are in parallel, they consume the same potential difference.